Analyzers of Mathematics, welcome to your Chapter 8 Lesson 2 notes, all about special right triangles. Right triangles aren't special enough. Having that right angle, there's even more special ones. Yay! Okay, so triangles, three sides, three angles, all add up to 180. Right triangles, one of those three angles is 90 degrees in measure, which of course is going to be the right angle and is going to be the largest of the angles in your triangle. It also is across from the largest side, the hypotenuse side. If it's a right triangle, that large side is called the hypotenuse side. We learned about Pythagorean triples and the Pythagorean theorem in the last notes that we did in lesson 1, and we applied it to specific right triangle situations. We talked about how when we're talking in triangle terms, negative lengths of sides aren't a thing. So we don't talk about that piece. We talk about the principal root when taking the square root, right? And I mentioned casually how the Pythagorean theorem and the distance formula are the same deal. Well, here it is in action. This is where the situation comes from. So when taking a triangle and putting it on the grid like this and seeing that here is your right angle, right? This is a length of 3, this is a length of 4. What's this distance here? Well, it turns out this distance here is 5. Okay? Because in the Pythagorean theorem, 3 squared plus 4 squared is the same value as 5 squared. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. 5 squared is 25 right there. That's how many you would get. And see, because of that relationship, Pythagorean triples are amongst the special right triangles that we discuss in moving forward with trig work. Also, amongst those would be talking about special angle measures. So these are special length measures where the integers all are there. We don't have any irrational lengths of sides. Here are places where the measures of the angles are what make this special. So you will have an irrational length of a side as a result, but your angles are 30, 60, 90 or 45, 45, 90. So this relationship is really important. And I know that you studied these in geometry, but moving forward, we're going to put these relationships, the Pythagorean triples and the 30, 60, 90, 45, 45, 90 right triangles into practice in higher levels of trig than you've worked with previously. So we have to recall what is the proportionality of the sides and how do I figure out the lengths of the sides when I know the angle measures. If I know I've got a 30, 60, 90 right triangle, the proportionality of the relationship of the sides of the right triangle are 1 radical 3, 2. Meaning the hypotenuse will be double the length of the small leg. So here's the small leg. This is the longer leg. That relationship to the small leg is multiply this value times radical 3. Okay, that's the relationship that we're looking at. So basically, you kind of need the small leg in this situation to figure out the other two. I will show you how if you're given the large leg, you can figure the other two. But you can always figure out the other sides if you know one and you know that you've got a 30, 60, 90. Much easier in 45, 45, 90 because the relationship is 1, 1 radical 2. Obviously, if two angle measures are the same, then the lengths of their sides will be the same. This is what we call an isosceles triangle, where because these angle measures are congruent, then their opposite sides are congruent. So a 45, 45, 90 right triangle is the only isosceles right triangle. Okay, that's the only isosceles right triangle available. And the relationship of the sides, if you know one leg, you know the other, and multiply that by radical 2, you got the hypotenuse. Okay, to really consider this guy, if you put another one back up to it, you've got a square. This is just the diagonal in a square. And so we've always kind of known that, oh, wouldn't it be perfect if a square, if a 1 by 1 square also had a diagonal length of 1? Look, got lots of perfect things that occur in nature. Irrational numbers, this is where they occur naturally, right? Using another irrational number, just like pi, just like e, these are naturally occurring situations where the value that fits the situation is a non-repeating, non-terminating decimal. And the safest way to write it is radical 2, right? 1 squared plus 1 squared is 2. Square root of 2 gives you the hypotenuse length. Hey, can't all be perfect, right? Unlike me. All right, let's apply it, right? Here are the basics. So here's 2 basic right triangles and how to consider it, right? Think of them as in a 45, 45, 90, x, x, x radical 2, or radical 2 times x. There should really be like a times there, so you don't think the x is under the radical. It's not. Those are being multiplied together. I'd really prefer that x to be in front of the radical 2. In a 30, 60, 90, it's x, notice, small side across from small angle, smallest side across from smallest angle, biggest side across from biggest angle, medium across from medium. Middle, I suppose I should say, right? So knowing the side across from the 30, multiply that by radical 3. This is times, right? So you get x times radical 3. Multiply that by 2, you get the hypotenuse length. Okay. Oh, that's the situation that we're looking at. Okay. So let's read these and again, think about those triangles above to consider the different relationships and proportionality of the relationships. Okay. So we'll fill in some blanks here. In a 45, 45, 90 right triangle, the length of one leg is 2. The length of the hypotenuse is 2 radical 2 because you multiply it by radical 2. That's the proportionality. If you know the length of the hypotenuse and you need to know the length of the legs in a 45, 45, 90 right triangle, then what you have to do is actually divide it by radical 2. Now, here's where our radical work comes into play. You can't leave a radical in a denominator, so you have to rationalize this. So radical 2 times radical 2 is radical 4. Square root of 4 is 2. 9 times radical 2 is on top. This is the length of that side. 9 radical 2 over 2. Probably should have left myself a little more space in that. Now, those were kind of easy with only one blank because if you know one leg, you know the other in a 45, 45, 90. 30, 60, 90, there's 3 different lengths of sides because these are isosceles. They're a little bit quicker as far as you only need to find the leg once. Now you know the other leg. If you have a 30, 60, 90, the length of the small side is 3. Oh, well, that's easy because hypotenuse is just 3 times 2. So you take that side and multiply it by 2 for the hypotenuse. That's 6. And you take this side and multiply it by radical 3 for the long leg. So 3 times radical 3 is 3 radical 3. Okay, so that's actually nice and easy. If you know the little leg in a 30, 60, 90, nice and easy. It's not always going to be the case, as we know, right? So if you know the long leg, what you do is take this value and divide by radical 3. So again, because we're dividing by a radical, we have to rationalize, right? Because that's the relationship. So we end up with 3 on the bottom and 8 radical 3 on the top. Now take that and multiply it by 2. which really just means multiply the top by 2, that's giving you the hypotenuse side. So 8 radical 3 over 3 is the small leg. Multiply that by 2, you get 16 radical 3 over 3 for the for the hypotenuse side. And that's if you know the long leg first. So that's we don't like the look of it, but at least it's easy to find. And lastly, if you know the length of the hypotenuse, have it. So divide it by 2 for the small leg. Now take the value of the small leg and multiply it by radical 3, 10 radical 3. Okay, so I knew the hypotenuse was 20. Divide that by 2 to get the small leg is 10. Multiply that small leg by radical 3 to get the long leg. I like to call that one the long leg because I love alliteration. Guys, I believe your fantabulous geometry teachers taught you these little tables that I will show you. If you know you got a right triangle and they give you one more angle, then you can easily figure out the missing angle, which of course in our case is 60. And the table that I believe your geometry teachers taught you was the 30, 60, 90 table, like this, where you do 30, 60, 90 across. And then what you do is x radical 3, and 2x. In 30, 60, 90, that's the proportionality of the relationships. Now fill in what you know. You know the little leg. Okay, 2 times radical 3 is 2 radical 3. 2 times 2 is 4. So u equals 4. That's the hypotenuse side. V equals 2 radical 3. That's the long leg side. We know this is a right triangle. We know one angle is 45 degrees. That leaves the other angle to be 45 degrees. That means that x and y are equal to each other here. So the table here is 45, 45, 90. X, x, x radical 2. So now I know this one, which means I have to go backwards to find the leg by taking 4 and dividing it by radical 2. Okay, which means I have to rationalize. So I'm showing my work off to the side here. I know I get 2 at the bottom. I know I get 4 radical 2 at the top, but 4 and 2 divide, and I get 2 radical 2 for both of these, which means x and y equal 2 radical 2, both of them, because they're both legs and they're both the same length. They're both across from 45-degree angles. They're both the same length. Again, make sure you repractice this with me because it's been at least a year since you've seen this in geometry, and it's really important that you know these relationships before we get to chapter 9 and chapter 10 and start applying these relationships very seriously. All right, why don't you guys try example 3 and 4? Speaking of you try situations, right? You try those. I'll come right back, show you answers, and then we'll finish up. Okay. So I showed the small amount of work that I had to do because really having the chart present makes all the difference in the world. Okay. Having the chart present is such a big deal, and I really like using that. And it's just a really great way to consider the other sides in a 30, 60, 90 or 45, 45, 90 right triangle. Okay. If you have any questions on doing this, let me know. Okay, we've got to make sure we know what those relationships are. These are another form of special right triangles. So 30, 60, 90, 45, 45, 90, Pythagorean triples like 3, 4, 5, 5, 12, 13, 8, 15, 17, what is it, 7, 24, 25, and 9, 40, 41. Good to know those first 3 of the Pythagorean triples, maybe not the other ones. There you go, special right triangles. Special right triangles. Okay. Make sure you work on those. Guys, I'll be seeing you soon. All right, let me know if you need something before we start sine, cosine, tangent. Bye.